Today we're talking about exponential functions. Exponential functions means a function where the variable is in the exponent. For example, something that looks like this: 3 to the power x, or 15 to the power x squared minus 5, right? These are exponential functions. The word exponential means the variable is in the exponent. I will say not something like x to the power 3. This is not an exponential function. I know there is an exponent, but we don't call that an exponential function because the variable is not in the exponent. This is a polynomial, and we already know how to deal with polynomials. Polynomials are very easy to handle, very easy to take the derivative. With an exponential function, there's a totally different set of considerations that you need to take into account. So the derivative of x to the third, we all know, is 3x squared. You bring the 3 down, you do the thing, you decrease the power by 1. What about the derivative of 3 to the power x? I'm just going to put a question mark. This is our topic for today. Can I just say it is not x times 3 to the x minus 1. You might imagine, can I just do the same thing? Bring the x down in the front, decrease the power by 1? The answer is no, you can't. These exponential functions, where the variable is in the exponent, they behave very, very differently from polynomial functions where the variable is downstairs, all right? When you have a polynomial, you do it like that. When you have an exponential function, you do not do it like that. Before we get into the details about the derivative of these kinds of functions, I wanted to show you how these functions are actually very common to encounter in the real world. Let's just do a very simple real world example. This is made up. I made up this example, but you can see it's very closely related to things that happen all the time in the real world. Let's say we have a pandemic. Does that sound familiar? Anybody ever had an experience with that? Let's say we have a pandemic in which, let's say, 50 people are infected. Like on day 0, at the beginning, 50 people are infected and the infection increases. So 50 people infected on time day 0. I'm going to measure time in days. 50 people are infected on day 0, and each day the infected population grows by 1%, all right? So in such a case, the way you describe this must be using an exponential function. I want to find a function, I'll call it f of t, which tells you the number of people infected on day t, all right? The infection is growing by 1% per day, okay? Right away, you can see this is actually applicable. This same kind of thing that we're about to talk about is the same as how it works in many other scenarios. In particular, like in economics, this is the way that interest works. Your money increases by a certain percentage over time. Interest rates, you get a little bit every month or something like that, all right? Anything really which grows according to percentages will generally be modeled by exponential functions. And, the spread of disease is one such thing. Anyway, let's find this function. Let's just write like a few sample values. What is f of 0? This would be the number infected on day 0, and I straight up told you that was 50. All right. What would f of 1 be? This is the number infected on day 1. There was 50. And then the infected population grows by 1%. So the populations infected will increase by a certain number, whatever 1% of 50 is. Now, 1% of 50 actually is 0.5 people. Let's just imagine that we're going to allow for fractions of people. In the real world, you would be talking about far greater populations of people, so the fractions don't really matter. Anyway, how would we figure that out? Here's the little idea. The amount, instead of multiplying by 1% and then adding it on to the previous amount, it's the same as multiplying 50 times 101%, right? There used to be 50. On the next day, there will be 101% infected. right? 100% for the 50 that already were infected, plus an extra 1%. Okay, so f of 1, I'm going to write it this way. It will be 50 times 1.01, all right? 101% of the what it was the day before. Now the new infection is 101%. Okay, what about f of 2? Well, to get f of 2, you would take this number, whatever it is. I didn't try to simplify this, but whatever this number is, and you multiply it again by 101%, because on the next day, you get another extra 1%. So f of 2 would be this same number, 50 times 1.01, times, again, 1.01, right? We multiply by 101% again. What about f of 3? On the third day, you take all of these people, whatever this big number is, and multiply it again by 1.01. All right? And so on. This is how you get this. Can you see a pattern here? Notice this guy is the same as 50 times 1.01 squared, isn't it? Because I have two of them. If you know, these parentheses don't matter because multiplication you can group things together. And what about this one? This one, I ran out of room over there, but this one would have 50 and then 3 of these, right? Times 1.01 to the third, okay? Can you see the pattern? What is f of t? F of 1 is 50 times 1.01. F of 2 is 50 times 1.01 to the 2. F of 3 is 50 times 1.01 to the 3. What is f of t in general? F of t will be 50 times 1.01 to the t. And there you see the variable inside the exponent. All right, this is an exponential function with this coefficient of 50. There you go. So in this example, what would, just in words, I don't mean as a number, what in words, what would this represent? F of 30, this is the number infected on day 30. And if you like, you could figure that number out. You do 50 times 1.01 to the power 30. You need to use your calculator for that. What would f prime of 30 represent? The derivative, now, we haven't talked about how you actually find the derivative, but what is the meaning of the derivative? This would mean the rate of change. How fast is f of t changing? That would be how fast is the number infected changing. So this is the rate of change of the number infected. Where does the 30 come in? It means on day 30. On day 30, how fast is the number infected changing? It's going to be increasing, right? Actually, there's a simpler way to say all this. I'll say i.e. this is the number of new infections. The number of new infections on day 30, right? How fast the number of infections is changing is the same as saying how many new ones do we get on day 30. Okay? So both of these things have very important meanings in the real world. So I hope it won't surprise you to know that people do care about derivatives of exponential functions. Ooh. There's a little formula for this, but I want to talk about just sort of looking graphically at this function, the exponential function. Now, if you graph a function like, let's say, a to the power x, where a is just some number, this is what an exponential function looks like. It has the x in the variable, and it has just some number down here. Such a function looks like, you can graph this on your calculator. You will see it looks like this, where it goes through the y equals 1 point right there. And it just increases. This side of it will increase quite steeply. That first version was a little too shallow, all right? This is what an exponential function looks like. I would like to let's try and draw the graph of the derivative. Remember we did that? Remember we used to do that? Draw the graph of the derivative. Now, when we did problems like that, we begin by looking here and trying to see where's the derivative equals 0, where's the horizontal slope. Actually, the derivative is not 0 anywhere here. The derivative here, you will notice, is always positive. Over here, it's like very slightly positive, very slightly going up. So I'll put some little p's over here. But then it gets more and more, and then eventually like extremely positive, very steep over here. All right, so what I draw down here, this is going to be the derivative of a to the x. it begins being very small yet positive, and then as I go to the right, it increases like crazy. It should look something like this. It begins very positive, but very small, very close to 0. And as I go to the right, it increases like crazy. All right? Something to notice when you look at these two pictures, actually, they look the same, don't they? They look the same. The derivative of a to the power x is, on a graph, actually, it looks the same as a to the power x itself. When I take the derivative here, the shape of the graph doesn't change at all. In fact, the derivative of a to the x is the same as a to the x. The only difference is you multiply by some constant. So I'll tell you the formula. Here's the formula for the derivative of an exponential function. Derivative of a to the power x, where a is some number, is the same thing again, a to the power x, but I said times a constant. Here it is. The constant is this. ln of a. This is the natural logarithm of a. Now, I don't know if you're into logarithms, if you know a lot about logarithms. It's not necessary to know a lot about logarithms. All you have to know for now is that this is a button you can press on your calculator and get some answers. So this ln of a is a number, whatever it is. You can compute this number on your calculator if you know what the a is. All right. We are going to talk in the future, I think next time, about logarithms in much more detail. So if you're uncomfortable with logs, we're going to get there eventually. But for now, just consider this is just some extra constant that comes on the end. All right? This is the formula for the derivative of an exponential function. You definitely should memorize this formula. Now, there is a special exponential function. One special value of a, and it is called the number e. E is a special number which is very important in calculus. The importance of e in calculus is kind of similar to the importance of pi in geometry. It has a specific meaning, but actually e comes up a lot in places that you may not expect it to come up with, just like pi does. Anyway, the number e. What is the number e? E is the number which makes ln of e equal to 1. All right? E is some irrational number, 2 point something something. I don't know the digits of e. But anyway, e is a special number. This is all you need to understand about e for now. The number e is a special number, and it has this value of the natural log. And so, if you are doing if you're doing exponential functions where this a is actually e, then this formula becomes very easy. It is just derivative of e to the x equals e to the x times, this would say ln e, but I just said ln of e is equal to 1. That's what e means. That's the definition. So, also put this one in the box. You got to remember this one. This one's very simple. It just says the derivative of e to the x is the same thing again. Yeah, great. Let's do some examples. Very simple examples would be something like, what is the derivative of 2 to the x? All you do is plug into the formula. Remember the formula, derivative a to the x is a to the x ln a, right? What do? It's just this, but a is 2. So I get 2 to the x times natural log of 2. And that right there, ln 2, is just some specific number. If you want to know what it is, you can plug it into your calculator, and that's what the number is. This is the derivative of 2 to the power x. If I had something like, this doesn't get any more complicated. What's the derivative of 10 to the power x? It's 10 to the x ln of 10. Okay? That's all there is to it for that. Interesting examples of derivatives of exponential functions will involve situations when it's not just a x up here. What if there's more complicated stuff up there? How about derivative of 10 to the power x squared plus 2x minus 7? How you like that? For this one, we have to use one of our rules, right? Remember the product rule, the quotient rule, the chain rule? This is not a product rule. Product rule is when you have two functions that are multiplied together. It's also not a quotient rule because that's when you have a quotient of two things. There's no quotients here. This is actually a chain rule. Chain rule is what you do when you have one function stuck inside of another function. And that is the situation here. We have this function, the polynomial, is on the inside. This is the inside when I'm going to do the chain rule. And then the outside is this exponential function. This exponential function on the outside, right? Outside. Right? So, we are going to take the derivative using the chain rule. We have the inside function and the outside function. How do we do the chain rule? I hope you remember. You take the derivative of the outside function, leaving the same thing on the inside. And then separately you multiply times the derivative of the inside. So I'm going to do the derivative of the outside function. That's this exponential function. I use this rule here, only the a is 10, and the x, instead of just x, is all of that stuff. So it becomes 10 to the same power up here times ln of 10. So what I wrote right there, this is the derivative of the outside with the same inside, right? This is what you do first part of the chain rule. You take the derivative of the outside function, leaving the same thing on the inside, which is exactly what I did. And then the chain rule says times the derivative of the inside, which is this polynomial, and that's easy enough. The derivative would be 2x plus 2. Put those parentheses there, haters. All right, this is the derivative of this. This is a little complicated over here, I guess. I mean, not so bad, right? Let's just try a few more. All right, how about this one? Derivative of 15e to the 3x. All right. Remember, our e one was special and easier than the other, right? All you got to do is, it's just the same thing again. Okay, what's the derivative of 15e to the 3x? First of all, this is going to be another chain rule because I have something on the inside, right? The inside is 3x as opposed to just being an x up there. Whenever you have anything in the exponent which is not just x, you're always going to have to do the chain rule in that case. What about the 15? The 15 is no problem. The 15 is a constant multiple in front of our function, and such a constant multiple simply exists in the front of the answer. Remember, you can always, when you're doing the derivative with a constant multiple, the constant multiple just stays like it is in the answer. So it's really just going to be 15 again times the derivative of this part. Now, you don't really have to draw this intermediate step here, but I'm trying to be clear in everything I do. Anyway, what about now? The derivative of e to the 3x. This one, we do the chain rule. So the outside function here is the exponential with the e, and I use the derivative of e to the x is e to the x. So I just get the same thing again, where instead of x, I'm using 3x. And then the chain rule says I got to multiply times the derivative of the inside of the exponent, which in this case is 3. And in this example, you can combine the 15 and 3 if you want. This is all multiplied, so it's 45 e to the 3x if you want. I don't care about that. How about this one? I got one more. Derivative of x squared times 5 to the 2x. This is a tricky one. This is a tricky one. What's tricky about it? It's not so tricky. What's different about this is you got to use the product rule. Here I have two things multiplied together. The first is x squared. The second is 5 to the 2x. I got to use the product rule. So I hope you remember the product rule. It's going to be the first thing, like it is, x squared, times the derivative of the second thing. The second thing is 5 to the 2x. I use this first rule here with the chain rule because I have an extra thing on the inside. It's going to say 5 to the 2x ln 5 times 2. This is the derivative of the 5, the exponential function with the 5. This is the derivative of the inside of the exponent. That was the chain rule that I just did there. Okay, remember, overall, I'm doing the product rule. It is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So I go plus the second thing like it is, 5 to the 2x, times derivative of the first part is 2x. There you go. That's the derivative. Just to finish up here, can we revisit my made-up real-world example about the pandemic that I started off with? It said f of t is 50 times 1.01 to the power t, right? This, remember, represents the number of infected people on day t. It starts at 50 and it increases by 1% per day. I say find and interpret f of 100 and f prime of 100. Find means actually figure out what it is, like as a number, the answer, find the mathematical answer. Interpret means say what it means in the context of this real world pandemic situation. All right, f of 100 is easy. For f of 100, we just plug 100 into this function. I get 50 times 1.01 to the power 100. And this you can plug into your calculator. I did, and I got 135.24. All right, so f of 100 is this number. What's my interpretation of that? That means, what does this actually mean in the context of this real world scenario? My interpretation is on day 100, that many people are infected. 135.24 people are infected. I know there's no such thing as 0.24 people. Don't worry about it. Okay, what about the other one? F prime of 100. This one is more difficult. For f prime of 100, first we must find the function f prime of t and then plug in the derivative. For f prime of 100, first we must find the function f prime of t and then we plug in t equals 100. So first I'm going to find f prime of t as a function and then we're going to plug in t equals 100. What do you say? What is f prime of t as a function? We have a constant in front and then an exponential function. So just like the one we did a few moments ago, when I'm taking the derivative, when I have the constant in front will just stay a constant in front of the answer. And then right here, I take the derivative of that 1.01 to the t. We use this rule right here. And we don't have to do any chain rule or anything because it's just the variable by itself. It's in the exponent. I get this answer over here using a equals 1.01. 1.01 to the power t times the natural log 1.01. And natural log 1.01, you can put that into your calculator. What I get is 50 times 1.01 to the power t. ln 1.01, I put that in my calculator. I got 0.00995. All right. And you can actually combine this with that on your calculator to make it a single constant. Like I always say, ordinarily I wouldn't do these simplifications, but this is a real world problem and I'm asking you to actually find the value. So this times 50, I did that on my calculator. I get 0.4975 times 1.01 to the power t. This is the function f prime of t. All right. Remember, our real goal was to find f prime of 100, which means you take this function and plug 100 into it. So f prime of 100 is 0.4975 times 1.01 to the power 100. And this you can plug into your calculator. I did. I got 1.34. All right. This is the derivative, f prime of 100. What's your interpretation of that? What does that actually mean? Remember, the derivative means the rate of change. This means how fast is the infected population growing? In other words, how many new cases are there on day 100? On day 100, the infected population was increasing by 1.34 people. So my interpretation of this is on day 100, you could say the infected population grew by this many people, or you could just say the there were 1.34 new cases on that day. That's what the derivative means in this case. That's all.